All right, what we are looking at, okay, what we're looking at now is a flame in space on the right, and a flame under the influence of gravity. And you remember we talked about um, different types of viscosity before, and kinematic viscosity, and that's kind of where this comes into play. So in outer space, you don't get the kind of flame shape that you're familiar with. You get the one on the right, which is just kind of an interesting teaser as we get into this. So this is a combustion reaction of methane, and I just wanted to start with this. So this is a pictorial illustration of a simple hydrocarbon, and you all have different backgrounds in chemistry, so just kind of bear with me on this. So this is a combustion of methane in atmospheric conditions. So you've got oxygen and nitrogen. So you've got mainly nitrogen. So the methane reacts with the oxygen to produce carbon dioxide and water vapor on the right, and lots of nitrogen on the right. So you're probably familiar with generally with this reaction. So this is a simple reaction. It's a simple hydrocarbon. And we're going to look at more elaborate hydrocarbons. And the reason we're looking at this is in the context of sustainability, moving on beyond air toxics and particulates into air pollution, but just combustion generally. So it's, again, to improve your level of sophistication when you discuss sustainability. So here we're focusing on air pollution. Now you can see one of the things, the nitrogen in the air doesn't change. This is diatomic nitrogen, N2, and it goes from cold nitrogen to hot nitrogen, which means that it just absorbs heat from the reaction. So it does nothing for you as far as creating energy, but it lowers the temperature because it's like a sponge. Okay, all you're doing is heating this nitrogen. It's not doing anything for you. Whereas the methane reaction is exothermic, so you're getting this energy, but also you're creating water vapor. And as you recall, water vapor has a very high specific heat. So it's a really big sponge. So if you want to make a hot flame, you don't want nitrogen and you don't want water vapor. And we'll look at that later. So this is, anyway, a good kind of pictorial. Now we'll look at actual chemical reactions. And we'll kind of do this in steps. So the first one here, let me go to the next slide. Whoops, rats. Okay, yeah. Well, the top one is a general hydrocarbon reaction. So say methane. So for any X or Y. And it's reacting with oxygen only, without the nitrogen, like I showed you in the diagram below. And the equation below it is with nitrogen. So in the case of the reaction without nitrogen, pure oxygen, like you get from an oxygen tank, you get the hydrocarbon plus the oxygen creates a CO2 plus the H2O plus energy. So it's pretty hot. Now this water here, this H2O is absorbing energy, so it is cooling it down a bit. But this is like when you deal with acetylene, oxyacetylene, for example. This is the type of reaction you get. And then if you burn in air, like you do with acetylene or a propane torch or burning wood, you get this kind of reaction below, which is what I showed you in the last slide. So here you're getting the hydrocarbon on the left plus the air. Now air has argon and some other trace elements as well, but it's mainly oxygen and nitrogen, of course. And you get CO2 plus H2O plus N2, and I threw in nitrous oxide there, okay? And we'll look at a little bit at nitrous oxide formation plus energy. So when you heat nitrogen, you get nitrous oxides, NO2, NO3. And they are an ecological issue. It produces acid rain and affects the aquatic ecosystem. So you've probably heard of nitrous oxides and, excuse me, NOx. And maybe you've heard of sulfur oxides, which we'll look at later, which are SOx. So sometimes you talk about NOx SOx, little cutie thing there. So anyway, that's this reaction, like I showed you in the last slide, but introducing this nitrous oxide term, it's NOx, which does arise. It doesn't become a big issue until you get real high temperatures, but it's always there when you heat up nitrogen, almost always there. Okay, and let's look at the next reaction. Okay, this is a bit uglier. Here I've added sulfur. You see where the mouse is? I've added sulfur. So that sulfur burns and becomes SOx, sulfur dioxide or sulfur trioxide. And so you get this NOx SOx creation, which is a common pollutant that we're concerned about. And this is an acid rain contributor, and it's a well-established concern in both air and water pollution. Okay, and energy. All right, continuing on. Okay, this is getting really ugly. So just trying to overwhelm you here on a Tuesday morning gently. So here you have the same reaction plus ash. All right, so these are inorganics of some sort, like silicone or something like that. So ash, I'm just putting anything that won't burn. And last time we talked about particulate matter, and we spent a lot of time on that, different sizes of particulate matter. Well, that's where this ash can come into play. Now, particulate matter can also be unburnt fuel, which we'll look at in a minute. It can be other things, it can be liquids. But here we're talking about, say, some minerals that just don't burn, and they pass right through the combustion process, and they come out the other side as fly ash or bottom ash. There's different names for them, depending on the size. You know, we talked about PM 2.5 and PM 10, largely, which are a big issue for respirable particulates that affect health. So ash is also distinctive because things can adsorb to it, like we talked about before. So bad actors can adsorb to the ash, and it becomes a vehicle to get it deep into your lungs. So if I want to get something deep into your alveoli, I have to attach it to a little ash particle. So it has some inertia and it gets drawn deep down. So it's a good way to convey bad things into your lungs, which is, you know, one of the issues with smoking. Okay, so we continue on. And okay, this is moving to a kind of a different direction here. And I know this is a lot to look at here initially, but it's this is the same reaction we looked at initially. Even in that diagram I showed you in the first slide. So this is burning a hydrocarbon in air, so it's got nitrogen in it. But we're doing it substoichiometrically, which means we're not giving it enough oxygen. So for every, say, methane molecule, there's insufficient oxygen to get full combustion. And we'll look a little bit at stoichiometry with nitroglycerin later on, because nitroglycerin is a fun thing to look at. So here's another case where you get air pollution. So substoichiometric is saying I don't have enough oxygen to combine with all the hydrocarbons. So what's happening here is that the hydrocarbon goes all the way through the process, and you also get carbon monoxide. Okay, so what I'm circling my mouse around are two additional pollutants: unburnt fuel and carbon monoxide. So when we look at combustion a little bit deeper here, you're going to see there's stages to combustion. So you've probably heard of the notion of time, temperature, and turbulence being an issue in achieving good combustion, complete combustion. And this is part of it, and I'll explore that later. So this is, again, we had these long reactions on the previous slide that included sulfur and ash and atmospheric nitrogen that turn to nitrous oxide, sulfur oxides, and ash, particulate matter. Here we're looking at when we don't have enough oxygen, and we also get unburnt fuel and carbon monoxide. So unburnt fuel can be a particulate matter as well. And we talked, again, that's a real problem in certain cities, especially in Asia. Okay, this is kind of the last chemical reaction we'll look at, and then we'll look at some other things here in a moment. This is burning pure carbon, burning your diamond, or anthracite coal, and we're an anthracite country in a way. This makes things really, really hot. So what you're doing here, when you don't have hydrogen, you don't get water vapor. So when you don't have hydrogen, you don't have water vapor. So it gives you only carbon dioxide. Carbon dioxide has a much lower specific heat than water. So the energy released is what it is, but the temperature on the right side of this equation is very, very hot. It's very, very hot. So even if and that's just the facts. There's no sponge to absorb things. Now, even if you burn pure carbon in atmospheric conditions, so you've got nitrogen in there, well, on the right side of the equation, you'd have CO2 plus N2 plus NOx, and they are a sponge. So burning in pure oxygen is going to give you a much hotter temperature than burning in atmospheric air, but it's still hotter than burning a hydrocarbon with hydrogen in it. So what I didn't put here was if I burn pure hydrogen, which is a big issue now in the news. If I burn pure hydrogen with oxygen, I just get H2O. I just get water. So, but it's a lower temperature. reaction. So, okay. And let's move on. So that was a lot, and you kind of have to absorb that a little bit. Here we're looking at Reynolds number on the x-axis and flame height on the right axis. And I just want to show you this briefly. This is laminar versus turbulent flow, so it follows you again, and it's kind of the good illustration how you get that initial laminar flow that we talked about in fluid dynamics, and then it goes turbulent. And you get a shorter flame when you have turbulent flow, and you see it's fairly constant. So turbulent flow is very good for combustion. You get good mixing of gases and you get a shorter flame. And designing for combustion is a geometry problem. So when you design a burner that fits within a certain, like with the big water tube boiler, you get this refractory that contains a certain volume, and that's what you have to work with. And your flame has to fit in that because you don't want impingement on the refractory that will cool it down and causing complete combustion. Okay, just a brief description of the exothermic reaction. There's an activation energy, this little rise here, to cause reactions to occur, and that's why you use igniters and matches and things like that to give the reactants sufficient energy to start the reaction. And then, of course, in exothermic reactions, they produce energy, which continues the combustion process. And endothermic is the opposite, so you're drawing energy in. And one thing that's interesting, we look at like the second law of thermodynamics earlier. Here, if you look at the entropy of the products, the randomness of the products, they're higher than the reactants. So you see this propensity to go from solid to liquid, liquid to gases, solid to gases, and increased volume of gases. So those are all related to the second law issue where things get more random. And okay, this is kind of weird in a way, but this is that simple reaction of methane, which is one of the simplest reactions you can ever see. And what happens though is there's a set of reactions that occur within the reaction. In other words, I a bit lied to you when I said methane plus oxygen gives you carbon dioxide and water vapor. There's actually all this other stuff, these intermediate products of combustion that arise. So you get this kind of decomposition of methane as it burns. So to get this reaction to go to its end, you need time. That's why you need time. And methane is a really light hydrocarbon. It burns easily. As you get into more complex combustibles, the time required and the intermediate products of combustion are even longer. So all this stuff has to happen. So it's not as if you kind of light a bomb and it goes off and you're done. All these reactions are occurring and they require time. So this is, I think, a good graphic to show you really what's going on. So again, I promise you we're not going to dilute what you're studying. So when we look at that simple reaction of methane and oxygen, well, this is actually the more honest and unfettered reaction, showing these intermediate products. Okay, and this is a flame temperature, or flame profile. So I got my little flame here. There's a flame. Okay, and this is a cross section of it. And I don't want to spend too much time with this because you can spend a lot of time dissecting this, which is good fun. But you see here it says the flame sheet on the left. And actually, I have this dissected on the next slide. Here's the temperature profile. So temperature is hottest at the edge of the flame sheet and is coolest in the middle of the flame. And here's the products. Oops, let's see. There's products and fuel. You see products and fuel. So if you look at the, well, let's see. What do I want to say about this? You see the fuel is burnt as you get to the flame sheet. It's all burnt up. There's no more fuel outside the flame sheet. And there's some products of reaction up to the flame sheet, and it continues a little bit on. You see the oxygen goes from atmospheric oxygen down to the stoichiometric point where there's no oxygen. So there's a lot here. So when you look at a flame, this is just a close-up of the flame. So I know this is really geeky, but it's interesting. So here at the end of the flame sheet, that's where your flame is hottest, because for every fuel molecule, you have an oxygen or sufficient oxygen. So every bit of fuel is burned up. You don't have extra oxygen, because when you have extra oxygen, that oxygen does nothing but absorb temperature. So the highest temperature is achieved as stoichiometric conditions when every fuel is consumed by every oxygen and there's none left after the reaction. Now in practice, you always have excess air. When you set up a boiler, you always have excess air because you want to make sure you don't have unburnt fuel. You don't have carbon monoxide or other unburnt fuels. And in fact, it can be dangerous. It can be explosive if that happens at an extreme. That's pretty extreme, but that can happen. And we'll look at explosions here later. So anyway, this is interesting. It's basically saying the hottest part of the flame is the edge of the envelope that you can see. Okay, and we talked about time, temperature, and turbulence. So you need time to run through those intermediate products of combustion. You need temperature to give an activation energy to start the reaction. And then turbulence gives you good mixing of the air and the fuel, which is important. Okay, this is nitrous oxide. This is an important graph because when you heat up nitrogen, you get in oxygen, you get nitrous oxide, which is a pollutant. Well, as you can see, it becomes a bigger issue at really high temperatures. Okay, so that's the facts. It's always an issue, but it becomes a real big one at high temperatures. So when you look at pollution control, whether it's for your car or a commercial power plant, there's these kind of judgments about when do you start intervening with nitrous oxide control. Okay, and then just a couple terms really quickly here. Detonation versus deflagration, and you can look at these links later on to see some videos that will enhance this experience. And so detonation, supersonic velocity, you get a shock wave. Deflagration is a slow burn, which is normally what you deal with. So it's subsonic. And okay, carbon, I talked about hydrocarbon, CXHY, this kind of generic presentation of hydrocarbons. And this is interesting. If you look at the number of carbons, generally if you have less than 4 carbons, it's a gas. As you move into heavier fuels, you have more carbons, as I listed here. So, these long hydrocarbon chains are things like paraffin, wax that you have in a candle, and crude oil and these kind of things. So that's just helpful. Okay, whoops on. And flashpoint is an important point. Lowest temperature at which vapor is given off at a sufficient rate to form an explosive mixture. Okay, so this is why you like diesel fuel in boats, because it doesn't blow up, it doesn't burn. It's really hard to get diesel fuel to burn. The flashpoint's very high. Gasoline wants to burn. Gasoline is incredibly dangerous. We use it all the time. We have an infrastructure to support it. We transport giant tankers on the roads. We bring in liquefied fuel right into Boston Harbor. We do all kinds of things with kind of really volatile fuels. Diesel is good that way. That's why one of the advantages of diesel, I'll say a safer fuel in a lot of ways. Okay, and then this, I'm going to show you a graph on this, so don't worry too much about all the words. But explosions, well, I shouldn't say they're good or bad. See, explosions are what they are. Sometimes they're good, sometimes they're bad. But you have these ranges of explosive limits. And I'm going to probably just show it. Let me just jump right to the next graph because that's better. Some of you, if you've ever worked with acetylene, like oxyacetylene, which you've done for brazing or something like that, if you know how dangerous acetylene is, and acetylene has woken me up a couple times. And here we're looking at the explosive range for methane and hydrogen. So methane doesn't want to blow up. There's a small range between 5 and 15% roughly where it will blow up, whereas hydrogen almost always wants to blow up. All right. So a little bit of oxygen, up to 4%, it will blow up. 80% oxygen, it will blow up. So hydrogen is really, really, really dangerous. So the wider these explosive limits are, the more likely a fuel is to explode, to detonate. So, and this is kind of interesting stuff, but it's why you have, like, if you lose a flame in a boiler, you do a purge cycle, because you're trying to get rid of like carbon monoxide and other unburnt fuels that could just blow up if you get this right mixture of fuel to air. And you do this, of course, in car engines. You have these explosions all the time. You're trying to get those. You do the same when you fuel a boat. You run a blower for a while to purge fumes out, and that's what you're trying to do, is avoid these explosive limits. So in design, you want to be cognizant of this, that if you're dealing with a hydrocarbon of some sort, there could be certain fuel-to-air ratios that are explosive. Okay, nitroglycerin, as I promised. And this is a big kind of ugly reaction. Now, this is a balanced reaction, so those of you who are familiar with chemistry recognize what I've done here. So all the oxygens on the right are balanced with the oxygens on the left, and the hydrogens and the carbon as well. But here's what's going on. If you think even back to the ideal gas law, if you look at the first bullet, one molecule of nitroglycerin produces 7.25 molecules of gas. So you remember PV equals nRT. Well, this is a sudden 7-fold increase in the number of molecules. Wow. Okay, so that's going to have an effect. If you look again at the ideal gas law, suddenly you have 7 times as many molecules. Now you can say they're smaller molecules or whatever, but you have these 7 molecules that are angry with thermal energy and they're bouncing around, and suddenly you've got all of these. So that's why this is so potent. Also, the fuel density, the amount of energy stored and broken by the breaking of chemical bonds. In the case of nitrogen, it's very high. So you've got a lot of potential energy in nitroglycerin. Plus, you get this huge volumetric change that I have a little time here, but this is a good place to pause, because most of you have seen a wood fire and you've maybe seen a coal fire. So what's happening with that is something that you may know, you may not, but it's not what you expect, I guess. So we'll consider wood. When you burn wood, you're not burning the wood. You're burning the volatiles coming off the wood. So you're devolatilizing the wood. So if you look at a flame, you'll see there's I don't know if this will work. You can see a gap. There's usually a gap where the fuel comes out. It takes a while for things to burn. In the case of wood, you're heating the wood up. You're driving these waxes in the wood out. You're turning them into a gas, and they burn. And if you think about looking at a fire, you'll see that the flame is above the wood. Well, so that's usually the combustion process. But then you get these glowing embers. So what is that? Well, when all the volatiles are burnt off, which are easier to burn, you're left with carbon, a lot of carbon. And the way carbon burns is the mass transport of the oxygen into the matrix of carbon. So the oxygen in your air, when you're burning wood or coal in this image, the oxygen has to get into the coal, into the charcoal briquette, sort of what's left of the wood. So it glows. It's oxidizing. It's very, very hot because you're not producing water vapor as much. So key points. So it's a 2-step process. First, you're burning the volatiles, the hydrocarbons, and they rise and turn to gases, ignite, burn fairly easily, unless the wood's wet. And once they're burned off, you're left with glowing embers. And those are burned by the oxygen moving into the carbon, because carbon does not turn to a gas. It doesn't volatilize. It's solid. So the oxygen has to move into it. Now, commercially, you can blow air into coal or whatever to get better burnout. You can pulverize coal, for example, and that's done all the time. You break it into really small pieces and shoot it out, and so you have a lot more surface area. So there's actually a little diagram here with what this looks like. This is for a coal, or this is a droplet or a coal particle, and you can see the solid breaking into little pieces and burning up, and that's kind of how particulates can burn. Okay, so it becomes a geometry problem. And it's interesting, sometimes when you think of chemistry and these sort of things, that often these can be geometry problems, like the shape of water, the polar orientation of water affects all sorts of things, from microwaves to reactions. And in the same vein, the shape of what you're burning can affect how well it burns. So small particles will burn better than large particles. But that's why glowing embers are so much hotter. You're not producing the water vapor. So when you think of mind stories, things to lock into your mind, if you look at wood burning, that's a great one, because you're seeing 2 steps. You're seeing the devolatilization, these hydrocarbons burning with their water vapor and all that stuff, and the buoyancy of the gases. And then you're seeing a solid burn and a mass transport of oxygen into the matrix of it. Okay, well, yeah, I guess that's where I conclude this. But before I do, then you're left finally with ash. So you have ash in your fire, you know, if you have a campfire, there's stuff that doesn't burn. Well, that's all these inorganics that we talked about before. So that's combustion, and there was a lot there. If you